Hey there, good morning. Welcome to another episode of the Relativity Company. Since we have been going over voltage sources and resistors, I think it's a good time to start talking about op amps or operational amplifiers. Operational amplifier is an electronic unit that behaves like a voltage controlled voltage source. So you have voltage going into the device and you have voltage going out of the device. So think of a operational amplifier or an op amp as a black box device that it's a when we say black box device, it means that we don't need to know what's inside of it just yet. However, we can send voltage into it and voltage comes out. So it's either amplified by a certain factor or amplified by and minimized by a certain factor. So if we think about transistors in general, transistors can be either a switch or an amplifier. So if we take a deeper look into an op amp, we'll find that there are transistors in it, and then they act and behave and interact in a certain way together to be able to amplify the signal. So here is an example of an op amp. It looks like an eight-legged bug, or almost like a spider or a beetle or a bug. And it's the figure here. Figure 5.1 here says a typical operational amplifier, courtesy of Tech America. So it's an active circuit element designed to perform mathematical operations such as addition, subtraction, multiplication, division, differentiation, and integration. So think of adding, subtracting, multiplying, dividing, differentiating in calculus, and integration in calculus or pre-cal. So if we take a closer look over here, typically your 8-pin chip has a inverting input, a non-inverting input, a V plus rail for positive voltage to supply, a V minus to negative supply rail to supply voltage, and an output and several balancing pins to make it more balanced. You have a non-inverting input here, inverting input here, non-inverting input here. This is the physical device that we're dealing with, and then this is the symbol, electronic symbol for the schematic. Okay, because the schematic and the board layout are two different things. The schematic shows the electronic behaviors of the circuit versus the board layout, which shows the physical, actual physical components that are connected together on a board. And if we look over here, we see that the difference between the non-inverting and the non-inverting input is there's a set resistance here, V2 minus V1. We don't really need to know too much about that right now because we're going to be going to LT-Spice and hand calculations later. V out equals A amplifying factor times VD, or the difference between not inverting input and non-inverting input. Okay, so what else? What else? Okay, so here is an example of using a 741, an LM 741, which is a all-purpose op amp, and then we have a supply voltage over here. We have two resistors, R1 and an R2, or our feedback resistors, so we'll call this RF instead of R2. And then we have currents flowing through this, and then it's going to amplify the signal at this output VO, and input is VS. Can you take a guess as to what factor this signal is going to be amplified by? If this is a R1 is 10 kilo ohms and R2 is 20 kilo ohms, it's going to be multiplying by a certain factor, and we're going to have to do some math to determine what that amplifying factor is. Typically for musicians and guitarists alike, especially guitarists, op amps are the active component in many guitar amps, vacuum tube amps, or sometimes called valve amps, and including overdrive pedals, distortion pedals. Fuzz pedals use a little bit different active component called a Darlington transistor, as I've learned, and overdrive and distortion are typically using op amps. So we'll see what this amplifying factor is by. So if we go to LT Spice over here, I was working on a circuit just before, so we're going to start on actually, I could start from scratch. However, for sake of time, let's just continue with this schematic. So press spacebar to get a fit view of the entire page. So we see that we have the op amp. This is a universal op amp, although you could use an LM741. A popular one for guitarists is an JRC 4558. That one is one of the best sounding, has the best total harmonic distortion, or THD. Some of these terms you don't have to know just yet. Just know that it sounds good and warm to the ears. And so we have this universal op amp, a VDD rail, VSS rail. This identifier is U1 because there's only one universal op amp. This R2 is 10K. This R1 is 1K. And actually, we're going to go by the book example and do 20K and 10K over here. So I'm going to rewrite this to 20K, 20 kilo ohms. Oops. 20 kilo ohms. And this one is going to be 10 kilo ohms. Okay. And then we have a VDD over here and a VSS, plus 15 volts and minus 15 volts to supply the voltage to go through the actual supply voltages, so that we can actually supply the voltage being sent in through VN. Excuse me. So we could do a dot operating point, except it doesn't make sense because this is more of an AC signal, alternating current versus DC. DC would make sense if it were all resistors and no op amp. You could do the DC operating point for this node over here and this node. Although we're gonna do nodal analysis with hand calculations afterwards. And so we have a 10 kilo ohm here and a 20 kilo ohm here. And what I can do is I can do a dot transient for 10 milliseconds, and we can see, this voltage source is going to be sending in 10 milliamps, at a frequency of 1K, 1 kilohertz. That's 1,000 cycles per second, and we're going to go like this. We're going to send we're going to run the simulation, measure the input voltage. And then you can see it's a sine wave with a cycle of 1,000 cycles per second, or 1,000 hertz, 1 kilohertz, and we have 10 millivolts swinging from 10 millivolts to negative 10 millivolts to 10 millivolts to negative 10 millivolts, 10 millivolts, negative 10 millivolts, and it goes on and on. And then if we measure at the output, we can see that the VN is in green here. It's green, and then in blue is the V out. So what can you determine about these two signals? Well, for one thing, you can see that one of the signals is flipped 180 degrees. That is because that we are going into the inverting input of the op amp. We're going into the inverting input of the op amp rather than the non-inverting, and the non-inverting is tied to ground. So when we send any AC signal into the inverting input at the output, we're going to expect that it's going to be flipped 180 degrees. What about the magnifying factor, the gain of the amp? Typically, when we think about audio or guitar amplifiers and guitar overdrive pedals, we think of gain. Gain is the factor of V out is actually V out divided by V in. V out divided by V in is the is going to be the closed loop gain, or in what the book was showing us as a factor of A times the difference between V2 minus V1. So if A is gain, what is the gain of this circuit, right? So V out divided by V in. Well, for a inverting op amp, it's going to be 20. Excuse me, I ran out of time on the screen recording app on Windows. So we can see that gain is A, the letter capital A, times the difference between the two inputs, V inputs. So for typical, let's see, if I can write a comment here, text, how do I do text? Text is a typical inverting op amp. A is going to be equal to negative V out divided by V in, or actually, excuse me, it's V out divided by V in is equal to negative R2 divided by R1. Negative R2 divided by R1. So then 20K divided by 10K is going to be 20 divided by 10. Well, let's see, that's 2, the factor of 2. And it looks like this amplifying factor is amplified by a factor of 2, as well as being inverted by 180 degrees. So that sounds just about right. V out divided by V in is the gain. And since it's a negative in front of this R2 divided by R1, that the negative signifies that the signal is flipped 180 degrees. Right? Okay. So we're going to do some hand calculations and see if that's correct. We're going to do nodal analysis. Okay, guys, so I'm going to be doing some hand calculations on I would actually do them on pen and paper, but I'm going to do some teaching exercises on this iPad over here. Great device. One of the best devices from Apple, actually. So if you follow along here on this page, I'm going to be recording the screen. So we have V out over here, we have V in over here, and we have two nodes. We have this node over here, and we have this node over here. So if this node is V out, and if this node is V in, and we want to do a nodal analysis, so if we call this node just any node like VA or VA, okay? Let's do a current going this way and a current going this way. This is going to be called I1, and this is going to be called I2. Okay, I1 is equal to V out. I1 is equal to V out minus VA divided by R2. I2 is going to be VA minus V1, or V input, over R1. So then, if I move this, let's see, if I close this and I move this out of the way, And on this page, let's see. V out, V out minus VA divided by R2. And since there's a node there, so one of the rules that we work with currents going into a node is that it's going to be equal to 0. So if the current going from the output is equal to the current going from the input, then we can set them equal to each other. Equals VA minus VN, VA minus VN divided by, how do I move this page? R1. Okay, so we're going to have to isolate V out and V in together so that the equation equals V out over V in. So let's see. VA is going to be 0. So then you can say this goes to 0. You can say this goes to 0. So it's V out, simplify, R over R2 is equal to minus V in over R1. So remember, we can do cross multiplication to get them on the same side. V out times R1, V out times R1 is equal to minus V in times R2. Okay? So now we can do divide by both sides. Let's divide both sides by R1. V out is equal to minus V in times R2 divided by R1. And then divide the other side by V in to isolate V out divided by V in. V out divided by V in, or A, is equal to, A is the gain, remember? A is the gain. V out divided by V in is equal to minus R2 over R1. And if we look back at the resistor values, the numerical values, it's going to be 20K divided by 20K divided by 10K minus 20K divided by 10K. And then that is going to simplify to minus 2. There's a gain of minus 2. Gain A equals gain equals minus 2. Okay? Thank you for tuning in, and I hope you have learned from this screen recording. Thank you to Camtasia and to LT Spice.